So in the last lesson we were looking at polar molecules and non-polar molecules, and we focused a lot on the examples with non-polar ones. So this lesson we'll look at polar molecules. So just remember that we need to look at whether there's electronegative atoms in the molecule, whether these are going to form dipoles or polar bonds in the molecule, and then we need to add them all together and make sure that the molecule is not symmetrical to get a polar molecule overall. So for example, we have water, which we know is a polar molecule. So why is it a polar molecule? First of all, we look at whether there's any electronegative atoms in here. Yes, because oxygen is electronegative. So oxygen is going to attract the electrons more closer to it compared to the hydrogen atoms. So it's going to pull them away, making the oxygen slightly negative compared to the hydrogen slightly positive. So each of these OH bonds are going to be polar. And when we add the vectors of them together, so the vector is the direction and the size of the pull. So we write them as the arrows here. So the size is like this, and the negative side is going to be at the head of the arrow, positive at the beginning of the arrow. And we're going to add them together and the direction and see if there's going to be any net dipole. So we add them together to get the net molecular dipole. So water molecule is a polar molecule because when we add the two together, we're going to get a net dipole up towards the oxygen. So when we draw here a line, we can see that the molecule is not symmetrical, and then we can say that the oxygen is pulling a lot of the electrons closer to it. So it's going to, this side of the line is going to be more negative, and then this side with the hydrogens are going to be more positive. So we can then say that the whole molecule is going to be a polar molecule. So we can show this physically that it's a polar molecule because when we hold here a charged rod, the charged rod is going to have a negative and a positive side, and this is going to attract the opposite side of the water molecule, whether it's the polar positive or the polar negative side. So when we hold it next to a stream of running water, a thin one, we can get attraction between the polar molecules and the rod, and this causes the stream to, rather than go straight down, it's going to deflect towards the rod. So another example which is really similar is hydrogen sulfide. So hydrogen sulfide atoms the sulfur atoms are going to attract the electrons closer to it compared to the hydrogen, because we know sulfur is more electronegative than hydrogen. So each of the H and S bonds are going to be polar, similar to water. We can see here that sulfur is going to pull the electrons closer to it compared to the hydrogen. So the hydrogen has a slight positive charge compared to here with the slight negative charge. If we draw a line, we can see that happens on both sides. So this end is going to be more negative than this end. So we look at each of the arrows, we can show the vectors as being towards this way. So each of the arrows are pointing towards the negative end of the bond. And then when we add these two together, we're going to get a net dipole, remember? So each of the bonds are polar, we said, first line here. And then next we add them together, get the sum of the vectors, and see if there's a net dipole. In this case we get it because this end of the molecule is slightly negative and this end is slightly positive. So we can say that the net dipole is this way, like the arrow suggests. And therefore, we can say that the whole molecule is going to be a polar molecule. So NH3 is also a polar molecule. We have to first look at whether there's going to be any electronegative atoms. Yes, nitrogen is more electronegative compared to hydrogen. So each of the bonds is going to be a polar bond. So we have 3 bonds here, and each bond is going to be polar, with the negative side being at the nitrogen and the hydrogen being positive. So each of these 3 arrows are pointing in those directions. So when we look at the molecule, is it symmetrical or not? It's not, because when we look at along the line again, we can see that this end is more negative and this end is more positive. So when we add these dipoles together, we're not going to have a net of 0, we're going to have a polar molecule. So the whole molecule is polar because one side is more negative, one side is more positive. And last example is CH3 Co. This one is a bit more complicated. We know that chlorine is a more electronegative atom compared to carbon, so chlorine is going to pull the electrons closer to it compared to the carbon atom. But also, we know that carbon is slightly more electronegative than hydrogen. So the carbon is going to pull these electrons from the hydrogens closer to it. So there's going to be a pull from here and a pull from here, and almost no pull from here. So the molecule is a tetrahedral molecule. Usually these molecules are symmetrical if they all have the same atom bound to the central atom. But in this case we have 3 the same, but 1 is different, so it's not symmetrical in this case. So the vector sum of this is not 0 because it's not symmetrical. We know that this bond has a slight negative charge here compared to here, and then these bonds have a slight negative charge here compared to here. So we have 2 planes that we're looking at. This one's going to be negative, this one's going to be negative, this one's going to be positive. So in this case, all the electrons are being pulled towards the top of the atom, and therefore we get a net dipole here of going up. So in this case, the whole molecule is nonpolar. It's polar, sorry. So the whole molecule is polar, we said, because it's not symmetrical and there are a lot of different polar bonds inside. So just to recap, we have to look at the electronegativities to see if there's a polar bond, add the bonds together, and then see if the shape of the molecule is symmetrical. If it's symmetrical, then it's going to be nonpolar because they're going to cancel out each of the polar bonds. And then if they're going to be not symmetrical, like in these cases, it's going to create polar molecules. So now that we know this, we can answer a few questions. So question 6 is to indicate the polarity of the NB bond with polar arrows. So remember, polar arrows, we have to point towards a negative direction. So in this case, do we have any electronegative species? We do. Nitrogen's really electronegative. So that means we're going to have slight negative charge over the nitrogen. That means the arrow is pointing towards the nitrogen, the negative end. What experiment can you conduct to show water is a polar molecule? So we looked at that with the stream of running water. We get a charge rod, hold it close to a stream of running water, and then it will deflect. So it's going to be attracted towards the polar rod, all the polar molecules, and therefore the water, instead of running straight down, we're going to get it to move whichever way we hold the rod. So question 8, water is more polar molecule than hydrogen sulfide because A, water molecules are bent, hydrogen sulfide molecules are linear. This isn't the case because we know that hydrogen sulfide has 2 sets of lone pairs. This means it looks like water, and therefore it's also going to have a bent shape. So this one is incorrect. The nuclear charge of oxygen is less than the nuclear charge of sulfur. It's not. They're all in the same group, so that means it's going to have the same charge. C, water molecules have hydrogen bonding. Hydrogen sulfide molecules have dipole-dipole bonding. Well, it's not the case because we know hydrogen bonding is between a really electronegative small atom, so nitrogen, fluoride, oxygen, and they're bound to a hydrogen. And then this dipole can then bind to a lone pair of electrons. And we know that in water, there's 2 sets of lone pairs, and hydrogen sulfide, there's also 2 sets of lone pairs. So it's not this one. So the difference between the electronegativities of hydrogen and oxygen is greater than that of hydrogen and sulfur. This is correct because none of them have the same same value of electronegativity when we look at the table. So we know oxygen is higher than sulfur. So it's correct in this case. So we know it's not hydrogen sulfide is not bent. It is bent. It's not linear. And it's got polar bonds, but it's just not as electronegative as the other one. Question 9. What 2 conditions are crucial for a molecule to be polar? Remember, we need 2 criteria to be filled. 1 is a molecule must contain 1 or more polar bonds, otherwise it can't be polar if there's none present. And then next, the molecule must not be symmetrical. If it's symmetrical, they all cancel out, and therefore it's non-polar as well. So question 10. Why is NH3 a polar molecule? We need to look at the molecule. Does it have any electronegative atoms? Yes, nitrogen is more electronegative than hydrogen. And then are all the bonds polar? Yes, all the bonds are going to be polar in the direction of the nitrogen. So arrows point to the negative side. And because the molecule is not symmetrical, we can see that because if we draw a line here, it will be more negative on the top, more negative on the bottom. So that means the vector sum, when we add all the polar bonds together, we're going to have a dipole that is not equal to 0. It's going to be net negative charge towards the nitrogen, net positive charge towards the hydrogens. So therefore the whole molecule is a polar molecule. Question 11. What factors must be considered to decide whether a bond is polar and whether the molecule is polar? So we need to look at bonds and the whole molecule, the addition of all the bonds. So a polar bond is one where there's an electronegative atom, and therefore it's going to pull the charge closer to it in a covalent bond. It has to be a covalent bond. And this is because it's more electronegative. It likes the electrons more, it's pulling it closer to it. So it's going to have a net negative charge. So a molecule is polar if all the polar bonds do not eliminate each other. So it needs to be not symmetrical. If there's asymmetry, that means it's not symmetrical, we can then add them together, and therefore it's going to have a net charge one way. So one side will be more positive than the other, and that means one side will be more negative than the other. And when we find this, we can say that the molecule is polar or not. So we need to look at the symmetry, and we need to look at if there's any polar bonds. So to recap, polar molecules require polar bonds in them, and then they must not be symmetrical, because if it's symmetrical, then all the polar bonds will cancel out. So if it's polar bonds and not symmetrical.